We are now going to look at a new way of defining functions called piecewise defined functions. So before we explain exactly what piecewise defined functions are, we're going to look at an example of a function where different conditions use different rules to determine the outputs. Then we're going to show how to express piecewise defined functions, how to define them. And then we're going to show how to graph piecewise defined functions. So piecewise functions, those are functions that arise out of situations where you have different rules for different kinds of inputs. So here's an example from our local movie theater. If you look at the prices for tickets, if you are below the age of 13, the prices are $7 each. If you are between 13 and 59, the tickets are $10 each. And if you're 60 and above, that is $8.50. So before I talk any more about this example, I should be able to explain why we can think of this as a function. In particular, I got to tell you what the inputs are and what the outputs are. So in this case, I'm thinking of the inputs as the possible ages of people, and then the output is the ticket price for a person of the age given by the input. So obviously, if you put the same age twice, you're not going to get a different ticket price according to those rules, which means that we actually have a function. Price is a function of age, which means that age is the input, price is the output. Now the sticky part about this is how do we express this as a function? There's not just one formula that works for all possibilities. We essentially have three different formulas. We have one formula for 13 years old, or I'm sorry, under 13 years old, and that is the output is 7. If you're under 13, it's $7 for a ticket. If you're between 13 and 59, the output is 10, and if you're 60 and above, the output is 8.5. So somehow we got to be able to define this function in a way that makes sense and that we know which rules that we use to get our output. So we need to be able to express three formulas with one function. So how do we do this? Well, what we're going to do is we're going to write the three formulas down and indicate which inputs go with which formula. All right, so f is the function where the inputs are the possible ages of movie patrons and the outputs are the prices for the movie tickets. And we're going to say f of x equals, the first thing we're going to do is draw this little curly bracket thing, and that is just an indication of, hey, we're going to be defining a piecewise defined function here. Then we're going to put in the three formulas. Now the formulas aren't very complicated, they're just constants, right? $7 is the ticket price when the age is below 13. Remember, x is the age, that's the input. If the age is below 13, then the output is 7. If I want to know when the output is 10, that is when the age is between 13 and 60. I should say 13 is less than or equal to x is less than 60, because you could be, if you're 13, you'll be paying $10. And then for 8.5 for the ticket price, that is when x is greater than or equal to 60. So you can see this is a nice way of expressing the function. Any x I give you, all you have to do is look where the x lies, look across from that, and that will tell you the ticket price. And those were pretty simple formulas. They were just constant functions, but we can do this with more complicated formulas as well. So for instance, if I did a piecewise function like this, that one looks pretty hairy, but it's not too bad. All that's saying is that we have two different formulas. And if you have an input that's less than 10, you use the one on top. If you have an input that's greater than or equal to 10, you use the one on the bottom. So for instance, if I wanted to find g of 2, I got to figure out, do I use the top formula or do I use the bottom formula? And what I do is I figure out how 2 compares to 10. Well, 2 is less than 10, which means we're going to use the first formula, because the first formula is for values of x that are less than 10. So g of 2 is going to be, well, my g of x is 5x minus 4. Plug in x equals 2. I get 5 times 2 minus 4, which is 6. If I want to find g of 13, 13 is my input. 13 is greater than or equal to 10, right? So that means I'm going to use the second formula, because the second formula is for all values of x that are greater than or equal to 10. So then I use the formula x squared minus 2x. Plug in x equals 13. I get 13 squared minus 2 times 13, which is 143. Now the only one that might be kind of sticky is, what do I do with g of 10? Because that is right on the border between the top formula and the bottom formula, but actually it's not as tricky as it seems because I have to use the same rule, right? So if I test it against the top formula, I can't use the first formula because if I were, I'd have to have 10 less than 10. 10 less than 10 is not true. 10 is not less than itself. It is equal to itself. So we can't use the first formula. However, the second formula, I need 10 to be greater than or equal to 10. That is true, so that means we can use the second formula. So I plug in x equals 10 into x squared minus 2x and end up with 80. All right, so now I want to talk a little bit about how we graph piecewise defined functions. And the thing is, the tricky part is, if you have a function like we just had, g of x equals 5x minus 4, and when x is less than 10, x squared minus 2x when x is greater than or equal to 10, well, sure, I know how to graph each of those functions individually. The first one is a linear function, right? We know how to graph lines. The second one's a quadratic function. We can do parabolas pretty well too. But the question is, how do I combine those into one function that satisfies the vertical line test and is in the spirit of what the function actually does? Well, let's first just graph the functions as they are, right? So on the left, we have our linear function. On the right, we have our parabola. And notice that the functions that I have go all the way, well, a little bit before x equals 0 and all the way out to x equals like 18 or something like that. But the idea is, in both graphs, it includes values of x that are not included in the function, right? Because remember, for g of x, that 5x minus 4 is not for all values of x. It is only for values of x that are less than 10. And for x squared minus 2x, that is only for values of x that are greater than or equal to 10. So if I want to graph those functions as they appear in g of x, I need to cut those graphs off at x equals 10. Only include the part of the line on the left where x is less than 10, which means I'm going to go to x equals 10, I'm going to draw the line, everything to the left of it, and I'm going to put a little circle at that point at x equals 10 to indicate, hey, I can't put x equals 10 into this formula because I only allow values of x that are less than 10. That point is not on the graph. Whereas on the right, I'm going to do the formula for x squared minus 2x, but in that one, I'm only going to include points that are x greater than or equal to 10. And I'm going to include that filled in dot to indicate that point is on the graph because the formula works for x equals 10 as well as x is greater than 10. And now if I want to do a graph of the combined function, I just take those two graphs and I put them together in one graph. They are the exact same graphs. Here, I'll show you. Those are the two graphs. And all I'm doing is putting them on the same graph together. The left-hand part of the line, the right-hand part of the parabola, and that is the graph of my function g. All right, so I think you're ready to do some work on piecewise defined functions. That is the file with the activities that is included with this video.